So we looked at, and this is a very similar example to what we have just looked at. Yeah. Methyl ethanoate and propanoic acid, same molecular formula, but their structures are very different. And also both their mass spec and their IR will appear different. Propanoic acid obviously has the O to H acid stretch and the C double bond O. Yeah. Whereas our ester only has our C double bond O and our C to H stretch. And there's probably a C to O stretch here, but we're ignoring that. Yeah? Right? Because the fingerprint region, yes, it looks a little bit different, but the number of peaks is fairly similar. Right? What would we observe from a mass spec difference? Going back to mass spec, what would you, like, what things would you notice with mass spec that would be different from one to the other? What's a couple of things you might notice? Right, you're going to have a CH3, CH2 peak. Yeah? What's that? That's 15 plus 14. You're going to have a peak at 29. Yeah? So this would have a peak at 29. This one wouldn't. Yeah? There's no way I can cut that would give me a peak at 29 for mass spec. What else might you see? We're not going to have two CH3 peaks, but what will that appear as on the mass spec? Right, the intensity, right? The intensity of the fifth peak at 15, we expect would be higher in methyl ethanoate because I've got two ways in which I can cut that CH3 off. Right? I'd also see that really characteristic 45 here. Whereas I don't have a way in which I can cut this to give me a peak at 45 in mass spec. So yeah, lots of different peaks that we would see because I can cut it in many different ways. Where's this not working? Where's my mouse gone? Okay, ethanoic acid, let's looking at this. Ethanol versus ethanoic acid. Ethanol, two distinct peaks, O to H and our C to H stretch, separate. You might see a little hump, right, like you see in butanol, right, in that worked example. We'll see that hump in between, but we've still got those two distinct peaks. So two distinct peaks, we're not too worried about that C to O stretch. Obviously, ethanoic acid, broad peak, little blip for our C to H here, and our strong C double bond O stretch around that 1700. So the thing to look out for is particularly esters that may also, ketones that may have a second functional group of an alcohol. And that's where we would see a C double bond O and two distinct peaks. Yeah, I think that has come up on a previous exam. Right? All right, use the IR data to identify peaks A and B. What does A correspond with? This is propanone. Yeah. Peak A corresponds with? What's peak A correspond with? C to H, yep. That's right, and peak B? C double bond O, fantastic. Yeah? So around 2900, C to H, around that 1750, right? C to O stretch. Okay, ethanol belongs to a group of organic acids. IR spectrum is shown on the right. Yeah. The broad absorption between 32 and 36 is due to the OH group of atoms common to all alcohols. Absorption just below 3000 caused by C to H, where the C to O stretch is around 1050. Explain how these two IR spectra confirm that both samples belong to the alkanol group of compounds. Both of these peaks. So, sample A versus sample B. Why do they belong to the same group, the same family, same homologous series? They've got the same functional groups, two distinct peaks. One 32 to 36, and 1 around 3,000. Yeah? Same functional group. Are A and B the same compound? No. Why? It's got a different fingerprint region. Fantastic. Yeah? Not the same. Both have characteristic different peaks in the fingerprint region. Exactly what you said. Excellent. Examine the structure and infrared spectrum of butane 2-ol. Which bonds correspond to the absorption peaks labels A and B? What's A? What's A going to be? O to H stretch. And B? C to H stretch. Fantastic. There we go. So peak A around 3,300. It's weak, it's narrow, it's O to H. Peak B around 3,000. It's strong, it's narrow, C to H. Yeah? So we should be able to describe the strength of the intensity, whether it's broad or narrow, and its approximate location. Deeper, generally, yeah. Okay. If it's not, then you should be able to describe it. But just be careful if you get a question like this that you're not ignoring it just because it's a weaker peak. Remember, anything above 1,500, you should be able to associate with a particular stretch. Here's another question. 2 IR spectra for compounds X and Y. One's a carboxylic acid, the other is an alcohol. Identify which is which, justifying your answer. Similar to the question we just looked at, or the worksheet, I should say. Straight away, you should be able to tell me. Carboxylic acid is the top. Why? Justify your answer. C double bond O and broad peak around 25 to 3,500. Yes, it doesn't have great intensity, but it's still a broad peak. Yeah. And why is this the alcohol? Yes, we have an O to H peak around 32 to 36. Right. What else? Or should I say, what's not here? No? What else is not here? Yes. Right? That's the two things you want to say. Broad peak here with the presence of C double bond O. Here, narrow peak here with the absence of a peak at C at around 1,700. Yeah? That's why it's not an acid. So that's what I would be looking for in a response. The absence of a peak means it cannot be an acid. Yeah? Cool. So two things, broad peak and strong peak around 1,700. Two distinct peaks above 2,900 and the absence of the peak gives us the answer. Okay, chem exam question. The IR wave number for bond stretching for C to O is lower than C to H. Which of the following best explains this fact? Oxygen atoms are more electronegative than hydrogen. Oxygen atoms have greater atomic mass than hydrogen. Oxygen have a greater atomic radius or have a higher nuclear charge. Who wants to have a guess? Have a guess? Who says C? You say C? It's not going to be radius. What does remember? Stretching, bending, vibrating. Mass. Has to be mass. Mass, not electronegativity. Mass. Only 21%, right? Greater mass means it's going to vibrate less, requires more energy. Think of it that way. Stronger the bond, yeah. That's right. Cool. Excellent. That finishes off 4 IR.